Good afternoon, everyone. Welcome to our presentation on latent security threats in modern software code logs. My name is Rrezarta Krasniqi, presenting this joint work with my student Banti Chakraborty Shruti from the University of North Carolina at Charlotte. Today we will explore how standard application logging creates a massive silent attack surface in software engineering. We begin with the logging paradox, which is to maintain high system observability, engineering teams require rich, detailed execution logs for error tracing and behavioral monitoring. However, this carries a steep hidden cost, which is a data exposure. So in practice, a log content usually contain the PI information like personal identifier information, user records, credentials, and sensitive API keys, which are routinely and inadvertently written directly into code logs. Now, when a sensitive line, such as the one above where it says pass equals 1, 2, 3, 4 is leaked, it creates three distinct architectural hazards. The passive exfiltration, which means the attackers breaching a log store a secret information without needing an active exploit. The second one is authorized abuse. The privileged insiders can scrape unmasked credentials to move laterally. And finally, the transitive exposure, which is shipping logs to third-party cloud services, pushes PI completely outside the defined security parameters. Now, this brings us to what we call the visibility trap. The traditional security mechanisms fail because of three converging blind spots. That is the context blindness, which is static tools parse text syntax rather than semantic meaning. The architectural brittleness, which means the hard-coded regular expression rules break the code structures or dependencies usually change dynamically. And scalability ceiling, which we call it, the final one, the manual rule maintenance simply cannot match modern deployment velocity. So to see this trap in action, look at the subtractive vulnerability. On the left side, in payment processor.java, a developer writes a standard logging line, which is pretty fairly simple. Static analysis tool scans it and sees no hard-coded secrets and flags it as safe. However, in upstream dependency on the right side, the transaction.java, a completely separate team member modifies the string mapping to print full card numbers during debugging. The downstream logging line in this case was never changed, yet it is now actively leaking data secrets like the full card number. Now, why do current tools fail? Standard secret scanners suffer from the deep content blindness, yielding up to 80% false positive rates on unstructured logs. Character level regular expression tools cannot differentiate meaning based on context. For example, a benign port number such as 8080 has the exact same alphanumeric shape as the tail end of the encrypted key. Because scanners cannot map these strings to semantic intent, 70% of analysts suffer from severe alert fatigue and ignore them altogether. Furthermore, studies have shown that 48% of active secrets are missed simply because variable names drift from expected patterns. And in other words, changing a variable name from db_password to an unmapped synonym completely bypasses standard rules. Then, as shown in the chart, as deployment frequency scales exponentially, manual rule converge flatness. When security processes slow down, software delivery, fast shipping inevitably wins, and rigid checks are bypassed or turned off entirely. Now, to eliminate these vulnerabilities, we propose a multi-layer semantic safeguard strategy. So, By pairing a structural rigor of graph neural network with a linguistic understanding of large language model, we introduce a three-pronged defense strategy: the taint analysis, the intent embeddings, and preemptive ID loops. The strategy 1 targets context blindness using GNN's static taint analysis. So basically what it means, by constructing a code property graph message passing neural network, it will track sensitive data flow from the source variables directly to log sinks. And because we trace the semantic lineage, renames or variable reassignments can no longer hide a secret. The strategy 2 resolves the rule breedenness using intent-driven embeddings. Instead of relying on exact words, tokens are mapped into a latent vector space. So what that means is that if a newly introduced variable clusters close to known high-risk fields, such as credit cards or keys based on cosine proximity, it is instantly flagged, independent of its lexical naming. And finally, the strategy 3 implements a preemptive privacy loop through a local IDE plugin. A localized small language model flags leaks in real time on the developer's machine and automatically suggests masking fixes before code is committed. Now, moving forward, the field faces 4 open challenges: a lack of labeled benchmark dataset, tracking leaks across microservice boundaries, reducing model hallucinations, and finally, balancing privacy redaction against practical log usefulness. Now, to wrap up, we should remember 3 key points. The log's risk profile is entirely dynamic and semantic, so it depends on data lineage, not the isolated log line. The traditional regular tools create a dangerous visibility trap, and combining structural graphs with localized LLMs allows us to make application logging safe by default. Now, thank you for your time. The full paper details and DOI are displayed on screen, and I'm now glad to answer any of your questions.